All right, so I guess roughly half of you in the room are already quite familiar with what I'm going to be talking about. So bear with me for the first few slides while I go over that for the other half of the room who has no idea what I'm talking about. So basically what I'm going to be doing is, as the other current PIs did for you, is go through a little bit of what I'm doing and a little bit of the story of how I went along with that and some of the interesting things that happened. And I'll end with a few lessons that I've come into that I figure I'd share with you to hopefully give you some insight into my process going through this. So I'm going to start off by giving you a very high-level overview of what it is exactly that I do. And I'll do this without throwing words at you. I'll just give you nice, pretty pictures to look at. So this is the world I live in. This is exactly the model that we're talking about. It looks very simple. We have 3 devices. We have a sending device, a receiving device, and we have an adversary. This is the beginning to every wireless security person's favorite model. What we do in this is we very quickly ramp up the game and make things very complicated. So we look at, we're not really interested in what can the adversary do with commercial off-the-shelf hardware. We might be interested in what the sender and receiver can do with commercial off-the-shelf hardware, but we're not really interested in that from the adversary's perspective because that's an artificial limitation on the adversary. Instead, we're interested in knowing what could the adversary potentially do given current state-of-the-art hardware and software. And answering this question 5 years ago was very different from answering this question now. So already some of the things that I wrote in the first draft of my proposal no longer apply. Because if you keep up with radio hardware, we now have software-defined radios that are the size of your thumbnail, essentially. So we're looking at interesting things that attackers can do with the wireless spectrum if they're given the opportunity to eavesdrop on whatever is happening in that space and interfere with whatever is happening in that space. The other assumption that we like to make is wireless devices typically aren't plugged into power sources. So we're often talking about things that are battery constrained. We might be talking about mobile phones. We might be talking about NFC devices or RFID devices. We might be talking about sensors that are installed in a building or on a person. So the kind of things that we started thinking about were getting away from some of the very simple models of my attacker is static and boring, my defender is static and boring, and we started thinking about what if these things were actually smart. And our motivation of doing this is actually looking at people. When people are faced with a situation and they've already made a previous decision, they don't just keep going with their same decision if something stops working. We stop, we think about it, we collect data, we make a new decision. We adapt. This is what makes us great. So what we decided to do is trying to formalize this in a way that the radio can be a little bit more human. So our model is, if you're familiar with the feedback system, this is exactly a feedback system. You yourself, you are a feedback system. So what we're trying to do is we're trying to say, my radio is now going to be intelligent. It's going to be allowed to make observations. It's going to be allowed to do optimization, and it's going to be allowed to make its own decisions. Currently, the radios in your laptop kind of do this. Your Wi-Fi has the ability to switch to a certain power level based on how far away you are from the access point. That's about the extent of its intelligence. We're talking about things that are orders of magnitude more sophisticated than that. So we're interested in looking at the algorithms for how do you learn what someone else is doing over the wireless medium. And I don't mean in the context of their data, I mean in the context of their behavior. How are they using that channel? What are they using it for? Are they using it correctly? Are they following the specifications? From the attacker's perspective, how can I violate the specifications? How can I violate what everybody says I'm supposed to be doing to interfere with you more effectively? And what kind of optimizations can I come up with to allow me to do this essentially in real time? So we did the work both from the perspective of the attacker and from the perspective of the defender. We did a little bit of modeling. I have a lot more pretty pictures I can show you. We did actually model our attacker as a wireless controller, taking information from whatever is observable and sending control signals back into the medium. This is exactly what a controller does, if you're familiar with control theory. Essentially, our attacker is attempting to control some sort of actuator, where the actuator in this case is the wireless medium. So we have a nice model for this where the attacker makes some observations. The observations might be wrong. The observations might be noisy. They might be incomplete. Does some analysis, comes up with some intelligence, and chooses a play from a playbook, from a strategy, and then iterates on this essentially indefinitely. Now, unlike a usual control system, we don't necessarily get to talk about things like convergence, because in order for a system to converge, it has to have a point that is stable. Wireless networks are not stable. They change all the time because it's nature. The sun changes your wireless networks on a minute-to-minute basis. So we often aren't talking about things like stability or talking about things like convergence. We're more interested in things like, can an attacker come up with a strategy that allows them to approximate something that looks like stability? It's an interesting point. So essentially what our first part of our work, we were looking at an attacker that said, I want to be able to block a certain n% of the packets that you're trying to send. Not necessarily 100%, maybe 5% or 60%. And I want to do that subject to an energy constraint, the constraints of what I can do in real time, and possibly a constraint on, as an attacker, I really don't want to be detected. So you can build in a lot of different constraints into the optimization, and I'd be happy to throw tons and tons of other charts at you to show you that, in fact, you can actually do this quite easily. So then we did a little bit on the defense side. Again, this is just an example of something we did in a software-defined radio. Again, incorporating feedback loops and controllers into the radio stack itself. So I don't expect you to actually understand what this figure is showing. Basically what we're showing is we can modify, in a software-defined radio, we can modify the control flow to include feedback within the radio architecture itself, to be able to adapt the signal processing on the fly in essentially real time. Now things start getting really interesting when you say, so I said we look at things from the attacker's perspective and from the defender's perspective, and we look at adaptation and optimization. The most interesting part of this in my mind is when you pit them against each other. You have an attacker who's trying to learn what the defender is doing and adapt to it, and a defender who's trying to learn what the attacker is doing and respond to that. So this is our model for exactly what this is. It's a dual optimization, convoluted feedback loop, and things that happen when you do this are very, very beautiful. Beautiful from the perspective that when you see the results, they're quite intuitive, but very difficult to actually model. So this is where we're spending a lot of our time lately. And actually, in the process, we created some tools. So this is a snapshot of one of our tools where we're looking at things like the effect of the attacker on the session that the defender is trying to use, the way that the spectrum is being used by the two different players, because they can play some fun games in terms of optimizing energy by minimizing spectral density. We can look at things like how accurate is the player's perception of what is actually happening. So the bottom left figure here is how wrong is the attacker in terms of what they think they're actually doing versus what they're actually doing. One of the interesting side effects in wireless is the attacker cannot simultaneously attack and try to figure out what was the effect of their attack, because their attack also blocks their own antenna, so they can't see their own effects. So as an attacker, I might ask the question of, I just tried to attack you, did it work? And in order to effectively adapt the attack from then on, you have to be able to answer that question. So we got to this point of having some preliminary results on all of our work, and we have this nice tool to help us try and understand. And this is the point where, we're a couple years into the project, we have some really nice early results, and then we started asking questions. And this is where things get really exciting to me, is when you start asking questions about your own work. So one of the first, and these aren't quite in order, we've asked ourselves a lot of questions and decided that we don't know the answers to some of them. So one of the questions that we asked was, these tools are great. Being able to at least visualize what's happening and understand what the different players are seeing is fantastic. But can we formalize this? Can we come up with something that looks sort of like an optimal strategy in terms of, I'm an attacker, I have this big of a battery, you're the person I'm trying to attack, you have this big of a battery, this is what you're trying to do, how do I optimize my resources to best attack this system? Or from the other perspective, I'm the defender, I have this much battery, and so on. So how do we actually formalize the interactions between these mutually adapting parties? And when we first started looking at this, we very quickly realized that's a big, nasty problem. And I think this actually came up during the mock panel review earlier today, that this is actually a big problem in game theory, or a big problem in control theory. And how would we ever do this as part of a wireless security research project? Well, the answer is we didn't do it by ourselves. We went to some of our friends who happened to be experts in game theory, people who solve poker for a living, people who actually model long-term games of Texas Hold'em poker and figure out how to give you the optimal strategy to win a poker game that a supercomputer can compute in a matter of a few days. So we went to them and we said, you know, we have this cute little wireless security problem. Can you help us model it as a game and give us a nice way to solve it? And a couple days later, they came back and they said, no, we can't. You've broken game theory. So what we thought was a very nice, simple toy problem in wireless turned out to be a nearly intractable problem in game theory, or something that had not yet been approached in game theory, I'll put it that way. So now we have this great new collaboration with some of our friends in the computer science department doing game theory, and we've actually worked out some interesting new tools and techniques for capturing things like the uncertainty and the error and the real-time constraints and the battery constraints, and building these all into a formalized game model to the point that for certain special cases, we can actually give you provably optimal strategies to play as the attacker or the defender for certain cases. When we relax some of the constraints, we're still breaking game theory, so we still have a lot of work to do, but now it's turned into a very fruitful avenue for additional research that spawned off the side of this project. Hopefully that's not my alarm. So the second question that we asked ourselves was, you know, a lot of our work is based on these players' ability to learn about each other, to collect information about each other. As the defender, I want to learn what the adversary is trying to do. As the adversary, I want to learn what the defender is doing so I can optimize what I'm doing. Well, so there's sort of a side question here. From the defense perspective, how do I hide what I'm trying to do? How do I communicate over the wireless medium without allowing someone else to learn the context around that usage of the wireless medium? This is actually a privacy problem. So we've identified an interesting new privacy problem around the fact that we've created these new sort of observation-based adaptive attacks. And this is something that we've spawned off as a separate problem. We're trying to work on this. It's very difficult. As you can imagine, with wireless, whenever you do something, it releases information about what you're trying to do. So trying to hide that information turns out to be a little bit of, well, are you sure you really want to do that? Maybe you should just not do that to begin with, and then nobody would learn what you're doing. That's the best answer we have right now. But in certain contexts, we have some really interesting results on how to hide unnecessary information and how to at least think about the release of context information or meta information by the uses of the wireless medium. So the next question we started asking ourselves is, okay, this is, you know, all this wireless security stuff is great at a really high level. What are some of the more domain-specific problems that we can talk about? So we started thinking about some of the specific application scenarios, and we quickly realized that they're actually completely different. When you start talking about wireless in the context of mobile phones versus wireless in the context of vehicles versus industrial automation systems, they're completely different problems to think about. They have such different constraints that you're actually solving different problems. Your formalizations look quite different. So this actually led to a whole sequence of new projects and new collaborations, the first of which we started talking about vehicular safety systems and how easily could we cause your cars to crash into each other when they're trying to do something like follow at a safe distance. Turns out that's really, really easy. So we have a new collaboration with one of the major auto manufacturers' research labs talking about this specific problem, which looks quite different from the general form of the problem. Again, we've been doing some work on wireless network control systems, and this is where you have controllers and actuators in different places connected through wireless networks. Well, it turns out if your controllers don't know that they're communicating wirelessly, they're never going to do the right thing. Also, it turns out if your wireless network doesn't know that it's carrying control information, control system actuation information, it's also never going to do the right thing. So this created a new collaboration with some control theorists and industrial partners around what we're calling co-design of wireless networks and controllers. So your controller is aware of the wireless network underneath it. Your network is aware that it's supporting control information. This wildly violates your lovely network protocol stack that you all learned about during your undergrad. But in essence, you can't solve this kind of threat without violating that stack. The other recent collaboration that we looked at was, again, a specific type of wireless. So in this case, we decided to look at telecommunications networks. And as soon as we started looking at telecommunications networks, we realized they're a wonderful, huge jumble of fun that have unfortunately evolved in very strange ways over the last several decades. And so we really decided, let's rethink the way that telecommunications networks are done, thinking about the fact that wireless security is an essential component, but it in fact is not independent of what's being done using that network, just as I said with the control scenario. So we decided, let's build our own network. We built our own network on campus. We have a couple cell towers, and that ambulance is also its own cell tower. It's tons of fun to play with, and now we have a great test bed for doing some of this really exciting research. And this is a huge collaboration that's coming to include a number of universities, at least 6 or 8 universities, and at least, I want to say, a dozen different major players in the telecom space who are getting involved in this project. So those are just some of the ideas that I have for you about creating collaborations and how collaborations just sort of naturally come out of your research if you continue to ask yourself these questions, these kind of what-if questions. So now if I have a couple minutes left, do I have a couple minutes left? 2. Okay. I have 2 slides of lessons learned, and I divided these into things that I learned in the process of writing proposals and trying to get awards. And the second one is things I learned, I guess, after getting an NSF award. So I'll go through these relatively quickly, and I'll let you think about them later. This came up a little bit earlier today, but I want to emphasize this. Ideas are great. You'll never get a grant without good ideas. Experimentation plans are great. They're even better than just having good ideas. Know what you want to do in terms of experimentation. Think about that when you're writing your proposals. But the best thing to have, in my experience and in my opinion, is some form of preliminary results. I can echo that by saying, look at the 2 proposals of mine that you read and compare them in terms of preliminary results. You'll see that one has none, the other one has a lot. That was an additional year of effort that went into that proposal, and I think that was the tipping point in my experience, in my mind. Second piece of advice I have is don't assume the panelists reviewing your proposal are experts on your specific problem. This actually came up on the discussion. I've seen a lot of panelists reviewing proposals who are familiar at a high level with what you're trying to do. They understand what you're saying, but they're not experts. If you throw a lot of really detailed math in there, it's beautiful, but they're not going to read it. If you can give insight goes further than math, in my mind. That's an opinion. Think about how you define success. Include some sort of a discussion in your proposal about how do we know when we're doing things correctly and how do we know when we've hit a stopping point. Some sort of evaluation plan or metric for your own project. Don't treat things like the broader impacts and, in the case of a career proposal, the educational component as afterthoughts. You should really treat those as an essential part of the work. If you write a very technical proposal and then you sit down for a day and think about what are the broader impacts of this work, you're going to have a really hard time. If you go into it thinking about this is the work I'm doing, what are the potential applications, what are the potential effects of this work, and it resonates throughout your entire proposal, the panel will see that, and they'll appreciate that. This also came up earlier, so I'm going to skip that one. And the last one, my last piece of advice is don't forget the story. Your proposal should flow. It should be easy to read. Panelists like when things are easy to read. If there's a consistent story throughout the entire description that you're giving, panelists really like that, and it helps them to understand, again, going back to the fact that they might not be experts on your particular piece of work. So this includes things like giving proper motivation, not assuming that your panelists are familiar with your related work, typical things that you see in a very good conference paper. All right, a couple last notes about post-award. Always question what directions you're going. That was sort of the highlight of what I had to say. Collaboration is awesome. I encourage everyone, even if you have a single PI grant, to try to form collaborations around that idea, because two people with different backgrounds can always create more interesting results than one person with a single background, again, in my opinion. And finally, a note that I wanted to add, build real systems. Especially if you do anything related to wireless or mobile, simulation only goes so far. In the fact of wireless, simulation is often garbage, and if you simulate something and it works really well, and then you put that thing into an actual radio, it's not going to do what you expect it to do. This is actually a learning opportunity for you and for your students to understand the differences between theory and practice. In my world, the difference between theory and practice is actually not just a little gap, it's huge. So this is very relevant for a lot of you. And with that, I will conclude, only a few minutes late.